Hey, everybody. All right. Last lecture, particle in a box. We're going to move to slinkies next week. We'll bring in slinkies. We're going to find that scientists are not very clever, and that, well, actually, they are quite clever. What we'll find is that the slinky is actually like a beautiful little toy to play with, both physically and quantum mechanically. It has some beautiful properties that I think some of the musicians will appreciate. The theory of the slinky and quantum mechanics is, in some sense, the most musical. I'm looking forward to that. What I want to do today is use particle in a box, some motivation to introduce the idea of spectroscopy. What is spectroscopy from the point of view of quantum mechanics? And this is not a rigorous or thorough analysis. It's rather a hint for you if you're in the dual degree program next spring, if you need an elective to come take spectroscopy with me, where you'll learn this in completion and then some. What I want to do today is justify what I would call the framework of spectroscopy. How does spectroscopy work underneath the hood? How do I know that I can use light to interact with molecules or atoms in a way that we appreciate or we do every day and take neglected? We kind of, in some sense, neglect the nitty-gritty details. My PhD is in those nitty-gritty details. This is the way that I like to think about spectroscopy, not as a tool, not as a means to an end for your analysis, but the heart and soul of chemistry as itself. My argument is, is that it's really not a trivial statement to say this, that light is the best way to study chemistry. Obviously, we find other ways to study chemistry. Use electrons and study electrochemistry and voltages and things like that. Of course, there's other ways to do chemistry and titrations and other types of chemical transformations, of course, but nothing is precise or as truthful or as, in some sense, unbiased as spectroscopy. It is the truth teller. And there really isn't an analog besides spectroscopy that will give you real answers, unbiased answers about what a molecule does. And so I kind of want to show you today the basic argument of spectroscopy. That requires us to do two things. One, we have to understand how our energy levels and our electron in our box functions. We've done a good chunk of that. We also have to think about light. We're interacting with particles and light. So we need to understand light first. So I'm just going to summarize electromagnetism in like 5 minutes. And what we're going to see is that in the limit of spectroscopy, the chemical limit of how we interact molecules with light, there's a lot of features about light that we don't really need. And I kind of want to show you that today. All right, so just some basic, very, very basic electromagnetism. Right, we just need to think about the wave nature of light in this situation. So we're going to consider an electromagnetic wave, call that an EM wave of wavelength lambda. Provides what's called an electric field, E, which is a vector field. It's a field of vectors. So each position in space, R, has a point in the electric field. Maybe there is some voltage there, maybe there isn't. And it also is time dependent. So time is a function. And it also provides a magnetic field. B, of R comma T. Oh, sorry, T is not a vector. Apologize. Okay. So anytime you have an electromagnetic field, you get both. Let's know that. And the formalism, the function of this wave, we can call it kind of like the wave, which is R comma T. It's a function R comma T is equal to E to the I. Right? Remember when we have E to the I think waves, sines and cosines. a number times k times r. Okay, so the r is multiplied by this factor k. You guys saw this. This is the wave vector. It's the same k that we saw in the free electron. And the system oscillates at some frequency omega times time. Okay, and we can write this out as basically, we need to add an amplitude to it. So A, there's some amplitude to the outside. So we have an amplitude to our field. And this is cosine k times r minus omega t plus I sine kr minus omega t. Okay, so we have a complex wave just like we do before, and we can identify each of these components as one part of the field. We say that the real part of the field is the electric component, and we say that the imaginary part of the field is the magnetic field component. Okay, so an electromagnetic wave is both an electric field and a magnetic field propagating in the same direction, but they're perpendicular to each other in a complex plane. One oscillates in the I plane, the other one oscillates in the real plane. So this is that wave that has two components. So if I were to draw it like on a picture, I have a vector that's pointing in the direction of k dot r. Right, that's the propagation direction in space of the vector of the wave. And there is a cosine component that is oscillating along in time. Right, it has a wavelength. Right, and it also has a frequency. And we can write that the frequency, I'll come back to that in a second. We'll come back to the frequency in a second. It has a frequency and how it oscillates in time. And that's the electric field. Right? This is the electric field. And then there's simultaneously a sine wave oscillating in phase in the perpendicular axis like this, which is the magnetic field. Okay, so that's an electromagnetic wave. They satisfy properties. There's two properties, well, there's lots of properties that the magnetic field and the electric field satisfy. They're called Maxwell's equations, but there's only two that we really care about for this. One is that the electric field dotted with the magnetic field is 0, which means that they're orthogonal, 90 degrees, which is how I've drawn it. And that the strength of the electric field is equal to the strength of the magnetic field times some scalar multiple C. Okay, and that's it. All right, so all this is saying is that you have two oscillating waves that are orthogonal to each other, propagating in the same direction, magnetic field in that field, and that their values, the strengths of them, are correlated. And you make one stronger, the other one gets stronger, and vice versa. That's all that is. Right. So they're independent, but they're correlated, right? They're connected, but they propagate in independent directions. All right, so let me just kind of think a little bit about this structure. This is a wave that oscillates in space and in time. Again, I've talked a little bit about what that means. Let me just remind you what that means. If we freeze time, right, and oscillate space, we froze in time. And what you're doing is looking at how, as you move along R, frozen time, you're looking at how the wave goes up and down in space. Right? So as I walk, it's up, walk down, it's down. And the wavelength, of course, tells me how long I have to walk until it's up again. So you can kind of think of that as the K is the space, KR is the spatial oscillation of the wave, meaning how much space it takes for it to oscillate. And omega t is where you stand in one place and let the wave wash over you. At some time, you're getting smacked by the wave. And other times, you're in a swell at some point. Sometimes you're in an ebb. Sometimes you don't feel the wave because it's 0. So that's the omega t is the feeling that you have at constant position. So you've got a wave that's oscillating in time and space. the question is do the spatial and the time oscillations matter to a molecule? Right? Because here's the problem. You can think now we have a particle in a box. We don't really know where it is. Right? We have some indication of where we think it might be, but it's not, it's delocalized. And now what I want to do is take a wave that depends on the position and interact with that particle, right? You can imagine that that's a really scary idea. Don't really know where the particle is. You might be able to know where the wave is, but correlating those two positions together is very difficult. So we need to be careful and make sure that we simplify things enough and that we have a reasonable prediction for what a wave looks like to a molecule. What we would ideally like is that we could get rid of the spatial dependence. Right? So we don't really care about where the wave is coming into the box. It's just that the wave is there and it's oscillating time. Right? That'll save us because then we don't have to think about position anymore. All right, so let's see if that's true. Can we make that approximation? All right, so simple calculation. All right, first we need to think about a molecule. What's the spatial extent of a molecule? Okay, well, remember that in a benzene ring, it's the first molecule that comes to mind. I've drawn it in such an awful way, but all right, the CHEM benzene. And you ask the question, what are the bond lengths, right? How often, what's the size of a bond, right? Of course, the bond length for these is 1.35 angstroms. And you could figure out that, the extent of benzene, right, this right here, is probably about 3 angstroms, give or take, right? So we could say is that the diameter of benzene, if we think of it as like a little ball, is kind of on the order of 3 to 5 angstroms, which is half a nanometer. Okay. So molecules are on the order of half a nanometer to a nanometer. Of course, you've got protein or something, they're quite a bit bigger. All right. But we're talking about little boxes or the molecules, if we were localized them, don't take up more than about a nanometer or space. Okay, so let's assume it's a sphere. And that means that the volume that the molecule fills up is about 1 nanometer cubed, which is 10 to the minus 27 meters cubed. Tiny amount of volume. All right, and we can go look at where, let's just take some experimental data and look at where benzene absorbs light the strongest, right? Let's look at a classic benzene example. And benzene absorbs kind of around 200 nanometers. So benzene has a very, very strong excitation, about 190, 200 nanometers. I think it's about closer to 220. And so typically for light for benzene or for organic molecules, lambda is on the order of about 100 nanometers. Okay, so it takes about 100 nanometers of distance to go from one ridge of the wave to another at frozen time. All right, so compared to the space in which the system is being filled, right? If you think about it now, what this is saying is that the volume of photons of the wave is 100 nanometers cubed, which is around 10 to the minus 20 meters cubed, give or take, right? So the wave in some sense takes something like 6 to 7 orders of magnitude per period of volume than the molecule does itself. So to the molecule, the wave just looks massive, right? To the wave, the molecule, the wave looks like you're 1 meter tall, pretty short person. The wave, the height of the wave when you're at the bottom of it, at an ebb in the wave, that wave is, top of that wave is 1 million meters tall. It's taller than, it makes the Burj Dubai look like a shorty, right? It's a massive scale difference. And so what does light really look like spatially to a molecule. It doesn't really have any spatial extent. So what you could say now, we can calculate this. We can go back to our formulas that we were talking about waves. We showed that K is equal to 2 pi over lambda. And so if we think about the product of K times R for this system, it looks like 2 pi over 100 nanometers times a radius of the molecule that's about a nanometer, right? Right, this is the molecule size. I'm just doing a rough number, right? Which is 0.06, right? So we can kind of say that basically Kr is 0. Okay, so the spatial part of the wave doesn't matter at all, right? And so what the molecule actually sees, the way to think about this system is here's the molecule, right? And all it sees is these giant wave fronts smacking against it at distance, right, that are all propagating at some frequency omega t, right? So these are just giant wave fronts. I don't care about how the wave oscillates in space, that, that it smoothly decays and goes to 0 and then goes negative, then goes positive again. None of that stuff matters to the molecule. Right? If you think about it, you're just getting smacked of 1,000,000-meter tall waves over and over again. Who cares about the ebb and the surges, right? All you care about is getting smacked in the head with something that's 1,000,000 times taller. So what we can say is that Kr is 0. And so we could just write the electric field as a function of time. Right? So what we could say is that the electric field, which is technically a function of R and T, really at this level just looks like a function of T cosine omega T. Okay? So we can treat the wave as just a time-varying wave. Okay? There are limitations to this. There are experiments you can do where the size of the structure is around the size of the wavelength. There, things start. Then you have to think about spatial. An atom, a laser pulse might be hitting one part of the molecule and not another part, and it excites it. It's more complicated than that, but you can tell that there is a way where this breaks down, and that's a very complicated and interesting part of spectroscopy, where you have to think about the space as well. But here we don't have to worry about this. We don't have to care about the time. Okay, so we have this time oscillating wave that wants to interact with a molecule. That's what we would like it to do. And so the question is what does the light interact with? So we've figured out what the interacting body is, which is the light. What does the molecule look to the light? How are we going to represent the particle inside of the box? How are we going to represent it from the perspective of light? Does light see? Well, we can start to think about that a little bit by realizing that what the light sees is just the wave function of the system. Right? Remember, in the end, waves interact with waves, and our system is defined with waves, so it seems natural that the light will interact with these wave functions of the states. So what we have to do is think a little bit about what wave functions to choose and construct a new wave function. Remember, the idea of spectroscopy is we connect two levels, a lower level and an upper level. So we're going to have two wave functions, a lower wave function, upper wave function. And whatever the light's interacting with is some combination of those two wave functions, right? It's the only thing that's happening. Two energy levels, two wave functions, right? So that's the only thing that's sitting in the box is that wave function. So that's where we need to focus. I want to motivate that discussion with an example. So what does a molecule look like? This is a really bad title, but you get the idea. What does a molecule look like to light? And what I want to do as an example is something that you've already visualized in chemistry before. I want to look at hydrogen. I gave this lecture in spectroscopy last week as well. It's just a copy of it, but it's a really nice insight. So let's look at hydrogen, right? So the idea of a spectroscopic problem is that we've got two energy levels. Right? Let's say this one is E1, energy 1, and this one's energy 2. Right? And it has a wave function psi 2 of x. And this one has one psi 1 of x. Right? And we want to define an energy difference between the two, right? That's the relevant quantity, E2 minus E1. Right? So how do we convert that into frequency? Well, we use Planck's law. Remember that Planck, we wrote this law down a few days ago, that energy is equal to h times the frequency of the wave, or h bar times the angular frequency. So this is radians per second. And this is 2 pi radians per second. So we have an energy difference. We can convert that into a frequency, right, which says that the frequency of this transition between 1 and 2 is the energy difference divided by h. Okay, so that's the nice thing is that we can always convert between energies and wave information however we please. We can even get a wavelength out of that. The wavelength of this would be hc over E2 minus E1. Okay, so we can always, if we know the energy difference, we can always choose a frequency or a wavelength of light that's the same energy as the energy difference, right? That's spectroscopy as you know it. So what does the molecule mean? What does the light see when it comes in and interacts with these two states? Well, remember, we need to think about the probability of where the electron is in the box. And so we're going to have to think about psi squared, the square of the wave function. Think about how the electron is distributed in these two states. And let's use hydrogen as an example, because you've seen these before. So the hydrogen atom. And what we're going to choose, well, the ground state is the 1s state, right? 1s. And then there are there's a couple of levels above, which is the 2s. And there's also the 2p states as well. Okay. Remember, there's 3 p states. I'm not drawing all the degeneracies here. There's 2 states that are the same energy. And so an excitation and hydrogen, the simplest excitation hydrogen is the connection between the 1s and the 2 levels. And as you can see, there's two different states it could end up in. It could go into the 2s or the 2p. They're at the same energy. So we kind of have 2 choices. Right? We could either go this way or go this way at omega 1, 2. Some energy omega 1, 2. And this is what's called, this in particular has a very famous name. It's called the Lyman alpha transition. Okay. And it's at, let me see if I have the frequency of it off the top of my head. I think it's 140 nanometers or something like that. Okay, we'll actually calculate it later in class. We'll actually look at the line. This is how often people look at stars. It's a really good way to do UV ultraviolet photography on stellar objects because they just glow like snow, like bright LEDs with this Lyman alpha transition. But you can see there's 2 different states that you can end up in. All right, so when I say I go from 1 to 2 in hydrogen, it's not really clear exactly if it ends up in the p state or the s state. And maybe you would say, okay, well, if it's s, then it's going to go to s. But in fact, that's wrong. It goes to p, and it only goes to p. The only thing that actually works is 1s to 2p. 1s to 2s does not work. Let's try to understand why that is. All right, there's a key lesson to be learned in this. What you find, I'll just rewrite that in a different way. That what you find in experiment, that 1s and 2p is what's called an allowed transition, meaning it's bright and you can absorb, it emits. And 1s to 2s is forbidden. Right? We have different terms for that. We sometimes call these allowed transitions bright transitions. And these are called dark transitions. Right? So interestingly, one is bright and one is dark. One emits and the other one doesn't. Let's try to understand why that is. the key point, the key lesson of this, the reason for this is tells you exactly how the light is interacting with the system. All right, so we need to think about what does the wave function of these connected states look like, right? What does the system look like when you connect these two states of light? And of course, all that is just a sum of the two states. So what we could say is that initially, so what we can do is before light, we say that the wave function of our system is just the 1s electron. It's a three-dimensional function at r theta phi. Let me give you a picture of it. I think it's nice to look at the pictures of these. And I'm just going to steal it from Google. I want these pictures. Please give it to me. All right, so the 1s orbitals, the psi squared of it is just a sphere. All right, we'll prove that later on in class. This is the psi squared for 1s. For the 1s orbital. All right, it's just a sphere. Okay, and the important thing is that it's a sphere where the wave function has the same sign everywhere. It's just plus everywhere. All right, so psi is plus. All right, it's always the wave function's always above 0. Right, so you have this plus orbital around and this of course tells you where the electron is in 1s. The nucleus is right in the center of this sphere. Right, so the 1s electron can basically just be anywhere in the sphere. And then let's look at then after light. We have two choices, right? We either are interacting between the 1s and the 2s. So we could have 1 over the square root of 2 of psi 1s plus psi 2s. Let's say plus or minus, could be either one. Or we can have a superposition of the s and the p. Okay, so let's look at the 2s and the 2p, right? So after we interact with light at omega 1, 2, right? We set the light to the right frequency. We're either going to be in a superposition of 1s and 2s or 1s and 2p. Okay, so let's visualize what those look like. Okay, so what we're going to do is look at the 2s and the 2p orbitals, and then start to think about how they combine together. So this is 1s. Let me give you the 2s. I'm going to give you a slightly different picture of it. This is the 2s orbital, psi squared. So this is the 2s orbital, psi squared. And the thing is that it's spherical, but you can see it changes signs. So there's a negative component here, and then in the interior, it's a positive component. Okay, so it changes signs in the middle. Right, so it has what do we call them? Fringes. It has two fringes and a node. Of course, since it's a sphere, the node is a donut or is a ball, a hollow ball in 3 dimensions. So instead of it being a point, it's a whole surface. But the sign changes. The sign changes. Okay, that'll be important as we'll see in a second. And then there are 3 p orbitals. Let me just give you one of them. They all kind of look the same. They're just rotated. And the p orbital, of course, has that nice slope structure that you guys probably are either fond of or not fond of. Psi squared, this is the 2p. All right, and the sign changes plus and minus here. Okay. All right, so those are our 3 orbitals that we're constructing our spectroscopic transition state, whatever you want to call it. We call it a superposition of the 2 states. And so let's think about what the net result of adding these together. What do the wave functions for these net states look like? So I'm going to copy this over, and I'm going to switch to drawings instead. But the important thing to note is that we're looking between, basically we're adding 2 spheres together, but here you have a sphere that changes sign in the middle. we're adding a sphere to a peanut, right? And so things are going to look kind of funky, but we're going to see an interesting behavior. So let's go ahead and paste these here. All right, so let's look at the 1s and the 2s combination, right? So 1s, and again, we're going to look at not psi squared, but psi. So we need to think about the signs. So 1s is just a circle. It's just a sphere. And 2s is like a sphere with a sphere embedded in it with a different sign. All right, that's 1s and 2s. Let's add them together. Okay, so what happens again when you add things together? We don't have to care about the difference. It's going to be basically the same thing. We'll just look at the sum. All right, where pluses and minuses are where they're different signs, they destructively interfere. So this wave is positive everywhere. I know I've driven it, it looks hollow, but it's not hollow. Every point inside of the sphere has a value. And there's a region inside of the sphere in the 2s that's negative. So what's going to happen is basically you're going to take this sphere, and when you add them together, the interior gets excluded. Because the negative part inside of this one cancels out the positive side part of this. Maybe it's easier if I draw another circle in here, but it's also positive. All right, so everything's positive. So the little interior cores cancel each other out. And the exterior says, so we get a hollowed out, basically the sum is a hollowed out ball. I don't know how to draw that. We'll try my best. So we've got this nice sphere. And then we have this region in the center that's 0. Right? Okay. So what I'm going to do now is I'm going to place this orbital on an axis system, right? Because the light is traveling in some direction. So let me put it on. So let's align this so that this is the z direction. And this is the x direction. And that the light is coming in directly along the z-axis. Right, so this is the light, and it's moving along the z-axis, okay? All right, so what does the light see? Well, the light sees electrons, right? It sees a ball of electrons, and of course, electrons interact with light. They're both parts of the electromagnetic interaction. Photons interact with electrons, vice versa. And as it passes through, right, it goes through some, interacts with some electrons and passes out. But if you think about it, both sides of this system are exactly the same. As I cut it along the x-axis, if I cut a halfway point as the light passes through it on the x-axis, the bottom side is the same as the top side. So what I can say is that what we could say in general is that the electron density is same in z plus plane, so above the xy plane, and in z minus. Right, the whole system is symmetric about this plane that I've drawn in orange. Right, so in some sense, if you think about it, there's equal amounts of electrons that the light sees on the bottom of the atom as it does on the top. Okay, so from the point of view of the electron, or sorry, the light, this is an isotropic density of electrons. It just looks like everything looks the same. It's just a sphere of electrons. All right, so what we can say about this system is that from the point of view, so the 1s plus 2s has no what we call polarization of charge along the propagation axis of the light. All right, and interestingly, what that means is that from the point of view of the molecule of the light, the atom, which again, it doesn't have any sense of the spatial structure. The light is so massive that this just looks like a point, a very, very small point, but it's a point that has no structure. It's just all positive. It's all negative charge, and it's everywhere. There's no difference which way you come into the atom. It looks exactly the same in all directions. And so what we can say about this state is that the 1s plus 2s wave function has no dipole moment. Remember what a dipole moment is. A dipole moment is a vector that tells you about how the charge changes in a system from negative to positive. Remember, so if I draw H2, right, these are both negatively charged in the same amount, and we say that the dipole is 0. But in HCl, right, we have a lot of negative charge on the Cl and positive charge on the H, and we say that this has a dipole mu, which is not equal to 0. Call that polar, right? Not. Okay. So H2 doesn't have a dipole, meaning that there's no distribution, a kind of like homogeneous or heterogeneous distribution of electrons where there's more on one side than the other. But HCl, of course, has it from electromagnetic differences. And what I can say is that this combination of orbitals also doesn't have a dipole. Right? Because it's this, you just have positive everywhere. Now, what about 2p plus 1s? A little different. Now I'll take my 1s, and I'm going to add to it my 2p electron, right? Which I'll just draw very roughly. It's that lobe-like structure. The lobes have some cylindrical symmetry to them. Yes. There's another lobe down here, but it's a different sign. So you have a negative sign to your phase and a positive sign to your phase for the 2p. And of course, 1s is positive everywhere. Now, can you see what starts to happen? If on this axis system I've constructed, when I add these together, the bottom half is going to get subtracted, and the plus half is going to construct. You're going to get a destructive interference on the south pole and a constructive interference on the north pole. So the wave function is going to polarize. There's going to be more probability electrons to be in the north pole than the south pole. So the tops have constructively interfere, and then the bottom halves destructively interfere. All right, so it's kind of hard to draw this net wave function, but I'll just kind of roughly do it for you. Let me draw my x-axis here, so I have a nice even line. But what we get is kind of a bulbous top. And then we get a negative decaying. It's really hard for me to draw this, but it kind of goes negative a little bit. It changes signs. And it kind of lumps in together like this. That's a really bad way to draw this. Maybe something like that instead. All right, it's a kind of a rough picture. It's actually the other, actually I have it, it's actually excluded because the lobe disappears, cancels it out. So I have it reversed. So it needs to be fatter on the edges than in the interior. It makes a hole in the center. Sorry, so let's see if I can fix that. So it's going to be fat on the edges because it doesn't get deleted like this. And then it's going to come in like this, and then it's going to have a negative region or something like this or something. I don't know. It doesn't matter. Okay, it's a really ugly shape. All right, maybe we'll do it on the computer at some point. Here's my point now. Now I propagate a wave in this direction. So I've got my wave coming down in the z direction. My wave, my electric field, E of t. And what does it see? Well, it sees more electrons on the top pole than the bigger pole, than the south pole, right? So we kind of, in some sense, have a positive charge build up here and a negative charge build up here because the electrons are more likely to be in the north pole than the south pole, the way I constructed it. Okay, and so what we can then say is that this combination of states has a dipole moment because there's an asymmetric distribution of electrons across the axis of the system. So what I can say is that there's a dipole now. Right? We've polarized. What we said is we've polarized the system, which means that we've moved the electrons in an asymmetric way, which means that the dipole mu for this 1s plus 2p is not equal to 0. It's non-zero. Very interesting. So the difference between these two constructions is that one has a dipole and the other one doesn't. Now, here's an interesting observation about dipoles. Right, the only time you often come across dipoles and electrical things, I mean, they're very common, but you always think about electric dipoles and molecules, like HCl. It's often more common to think about magnetic dipoles, which is like a bar magnet. It's got a plus and a minus, little magnets. And what happens? So you've got a bar magnet sitting in like on a board, and you bring in a permanent magnet. And what happens is as you move that permanent magnet around the bar magnet attracts the magnet. Right? So the magnetic field generates an electric field and a magnetic field, and then a dipole interacts with that field directly. If there was no magnetic dipole, it wouldn't interact. The whole reason why it interacts with that magnetic field, because there's a positive and negative end. So as you move that magnet around it, the positive and the negative tracks with it. Right? What happens when you do that in an oscillatory fashion? You just do this. You spin it. All right, so what happens is now you get that dipole spin. Right? If it's magnetic, what happens when the dipole spins? It emits radiation at the spinning frequency. So what happens when you get a dipole to oscillate with a field is that dipole starts to also emit light. It also starts to emit an electric field. Okay, so and that works as well for the electric field on the electric dipole. Remember, the magnetic field and the electric field are exactly the same thing, but they're perpendicular to each other. Right? They're the same but different. They have the same properties, sort of, more or less, but they're perpendicular to each other. And so magnetic dipoles interact in magnetic field exactly in the same way that electric dipole interacts with an electric field. So when you have an oscillating electric field, which we do, and it interacts with a dipole, the dipole will start to oscillate with the field. And when a dipole oscillates, it emits light at its oscillation. I'll write that down. So the goal, so spectroscopy is, well, the idea is classically, or well, I would say classically quantum mechanically. I'm just going to say in general, right? Because we're going to kind of mix and match classical ideas here. Is that a bright state, a bright transition, a bright emission or absorption corresponds to a superposition of two or more states, more energy states, that has a net dipole. Okay, net dipole. Right? It doesn't have to be a permanent dipole moment. Right? I just showed hydrogen in of itself. Hydrogen does not have a dipole moment, right? Because it's just a sphere of charge. But I just showed you that when you, and of course, if you look at the 1s state or the 2sp state by themselves, the pure energy states by themselves, pure states, they also don't have dipole moments. But when you start to add them together and you start to connect them together in superpositions, then they can polarize each other because they have different symmetries. Right? We just saw that with the 2p and the 2s. The 2p by itself has no dipole moment. The 2s and the 1s has no dipole by itself. But the combination of the p and the s has a dipole. So it's about constructing dipoles. All right, and the simple idea is this. Is that if you have an electric dipole, pointing in some direction, and you oscillate a field at it at omega t. So this is cosine omega 1, 2t. Then that dipole is going to oscillate in space around that axis at frequency omega 1, 2. Okay, so the dipole generates an electric field which is proportional to the electric charge of the electron times the strength of the dipole times cosine omega 1, 2t. So the dipole generates light by oscillating in sync with light field. Right? They start to do a dance together. Okay, so what that means is that any transition, any bright transition, must have a net dipole. It's kind of a repeat of the first point. I'm just going to repeat it again. Net dipole correspond in its combination of upper and lower states. Okay. Less 10 or 15 minutes that we have. I want to just do a small calculation. So the question I want to do now is I want to go back to the particle in the box, and I want to ask the question, what are the allowed transitions in the particle in the box? Okay, so we've looked at hydrogen, and I showed you visually that 1s to 2s doesn't work, but 1s to 2p does. And so now the question is, let's go back to particle in the box. Let's see if we can calculate a similar rule for the particle in the box. All right. This requires a couple of rules that we need. Just one more little tool that we need. And when I wrote these lecture notes, I went overboard. Holy crap. You guys should be glad I'm not giving you this lecture. Holy crap. Okay. All right, so let's look at the particle in the box. All right, so what I want to do is I want to calculate the intensity of an absorption or an emission based on which states are the initial and the final. Okay, so let's just do that. We have two states. They're somewhere in the band of states. And we have n equals I, the initial state, with energy EI, and n equals F with a final energy EF. Okay, and the energy difference between these is omega 1, 2, which is EF minus EI over H bar. Okay. Right. And the goal is, it turns out, this is something that comes from a very famous physicist from Chicago, actually an Italian Jew who escaped, and well, he's the first man to take uranium to go critical, created the first nuclear reaction, which is Enrico Fermi. And what Fermi says in very simple terms, we're going to kind of simplify his rule, called the golden rule. It's called Fermi's golden rule, which says that the intensity of the transition I to F, right, so this is the intensity of transition, right, how bright it is, how strongly it absorbs, is equal to the probability of starting in I and ending in F when interacting with an operator, which is the electromagnetic field. the dipole. All right, so he says that the dipole and the field, so dotted with the field, the dipole dotting with the field, which has units of energy, is the operator of spectroscopy, right? The box that we create is a light field. That's our box. And the operator of interaction is you take the dipole of the molecule and it interacts directly with the electric field. Okay, that's our experiment. And so what we want to look at is the probability that when we take a state and state I, and we interact it with the field with its dipole, which is mu dot E, and it ends up in the final state, which is a different state than the initial state. Right? What's the probability of that? Well, we know how to calculate probabilities. It's an integral. So what we're going to calculate is the integral over the box of psi f, our final state, star. Of course, they're real. We don't care about that. Times this operator, which we have to calculate, mu dot E, acting on the initial state, integrate over dx. I'm sorry, we need to square this. This needs to be squared. So we're going to take this integral with our two wave functions, and then we'll have to calculate this operator. It's really easy to do. And the idea is that if I to f is not 0, we say that this is a allowed or bright transition. Right? We see it in our spectrum. And if it's equal to 0, it's forbidden or dark. All right, let's just do a quick calculation. So the last thing we need to figure out is this operator. All right, and there's a really, really nice way to do this. This is the biggest fudge factor you'll ever see me do in this class, but it turns out it works beautifully. If you don't mind, I'm gonna go back just a page. I want to look back at these dipoles. Right? If we want to represent, remember the wave is much, much larger than the field, or sorry, than the molecule. So we need to think about what the dipole of this wave psi squared looks like to the molecule, to the wave, from the perspective of this very large propagating wave. Right? All it sees here is a dot of electrons. Right? But this isn't really a dot of electrons. It has some structure to it. There's a negative part and a positive part. Right? So what's the simplest function that we can write that would describe something that changes signs about the origin? And the answer is x, or z. So what I can write this dipole as is just z. It's a positive function above z, and it's a negative function negative z. And the slope is just the dipole. So what I can say is that the idea is that we can treat the dipole as mu, it's a function of r, as r plus r squared over 2 plus r cubed over 6 plus dot, dot, dot. That's a Taylor expansion, Taylor series. And what we're going to do is just say it's r. And we're just going to take the linear part. So this is called the linear dipole. Okay. And so the interaction, the operator for spectroscopy, the interaction operator, which is mu dot E, is equal to minus E times the R vector, direction vector, times cosine omega t, 1, 2t. Okay, and so if the system, if the light is propagating in the z direction, R is the propagation direction of the light direction. Well, so if R is z, then it's just equal to, or x, it's minus E dot x times cosine omega 1, 2t. It's that easy. It's just an x function. We've already calculated this, right? So Remember, we calculated the average position of the particle in the box, which is that we stick an X in between two wave functions. We've already done this math before. There's some extra numbers and some stuff on the floor, but it's all the same math. So in the end, at the very basic level, a spectroscopy experiment is using light to measure the average position of the electron as it transitions between two states. Right? Remember when we measured the average position of the electron, psi I and psi F were the same. Here we're adding some connective tissue between the two. And basically what we're looking at is how does the light propagate through the system in space to allow us, in some sense, to algebraically connect our two states. All right, so it's just a position measurement using light. I'll write that here. So this is a position measurement with light. So let's go ahead and calculate that. We have everything we need to do. We have a wave function, we have an operator, we have an integral, we have a box, everything we need. I just want to get my final notes up. Okay, so let's go ahead and let's just do a quick calculation. All right, so the intensity. How do I want to do this? Let's do it from n equals 1 to n equals 2. All right, we'll just do the basic one. All right, and it's going to be equal to the square, absolute value square of the integral from 0 to L of psi 2 of x times minus EX times psi 1 of x. Okay, so we can integrate this out. This is this 2 over L times minus E. That's the charge of the electron, by the way. It's just a number. 0 to L sine 2 pi x over L x sine pi x over L dx. Let me make this a little bigger. I'll make this a little larger so it's easy to see. And then we square that. All right, we can evaluate this number, but let's roughly see if it's, remember, we want to just check to see if it's forbidden or allowed. And we just got to make sure this is non-zero. If it's non-zero, then we expect to see some absorption if we connect the two levels with some light that's resonant with them. And there's a cosine, so there's also a cosine squared omega 1, 2t on the outside. We don't care about that because it's just time, and we're not looking at time at the moment. Okay. So anyway, let's just look at this integral. So it kind of looks like 0 to L sine 2 pi over Lx times x times sine of pi L over x. Pi x over L, excuse me, dx. All right, and let's think about the symmetry of these functions. Right, this function right here, L to 0 looks like this. It's a half wavelength. This one looks like a full wavelength. Something like that. Okay. So these are both odd functions. Right? And this is, no, wait, hold on a second. No, sorry. This one's even. Yeah, this one's even. And this one's odd. You have that flipped. No, that's right. It's even and odd. And this one is odd. X is odd. Right? So we have odd times odd, which is even. Even times even is even. So the overall combination is even. So this is by definition, so I'm going to square it, but it doesn't matter. It's not equal to 0. by definition. All right, we can calculate what the value is, and it tells us how strong the line is, the intensity of it. Don't care about that. Right, but what if I were to, for instance, right, so what we would say is that the n equals 1 to the n equals 2 transition is bright. We would see an absorption in our spectrum. Right? Well, what about n equals 1 to n equals 3? Let me make sure I have this section. Yeah. So what about n equals 1 to n equals 3? So the intensity of n equals 1 to n equals 3 is equal to the square of the integral from 0 to L of psi 3 of x times the product EX times psi 1 of x dx squared. And this is just roughly equal to, I'm just going to kind of fudge it a little bit. We don't care about the numbers so much. Integral from 0 to L of sine 3 pi x over L x sine pi x over L dx squared. All right. We just showed before that this is odd. This is odd. And it's not hard to show that this is odd. So the overall integrand is odd. And so by definition, this is 0. All right. You can go through this list arbitrarily and think, okay, what if I connect things that are 3 apart, 4 apart, 5 apart? All right. And what you find is that for the particle in the box, light induces a transition if, only if, delta n is equal to 1. Okay. It's not too hard to show that all odd delta n's are bright but weaker for delta n greater than 1. And then all delta n equals 2 transitions, or 4, 6, 8 even numbers, are forbidden. All right. So what we learn is that light does allow us to connect between two states. It gives us a non-zero probability, but they have to be states that give you a non-zero probability. They have to be states that what we say are overlapping, meaning that the wave function of this one times this little x here, when we overlap it with the final state, the idea is we kind of want to see how they gel together and connect together. They have to, the total product has to integrate in some non-zero value. And the only way that happens is that the difference in n is an odd number. So what we would see is we would see the 1, 0 to the 1 to 2. We'd see the 2 to 3, the 3 to 4, the 4 to 5. And then we wouldn't see the 1 to 3, we wouldn't see the 1 to 5, we wouldn't see the 1 to 7. But much weaker, we would see the 1 to 4 and the 2 to 5, right? The delta n equals 3, and so on and so forth. And we would see that spectrum as well. So there are patterns, right? So first of all, the idea is that we get patterns of lines that are all connected. Right? These patterns, these rules, right? These are hard rules. Delta n is equal to, it doesn't, you get 0 probability, there's no transition, right? So we have a name for these rules, and we're going to look at these every time we bring up a new model because they're interesting. They're called selection rules. All right. So the idea is that in spectroscopy, we can use light to bring some system from one state to another, but they have to satisfy certain properties, meaning that they have a dipole and that the integrand works out the way that you want it to. Everything is symmetric or even when you integrate. And these are hard, in some sense, very, very, very hard and rigorous rules for spectroscopy and all types of spectroscopy. What this tells us is the y-axis in your spectrum. Remember, the x-axis just tells you the energy differences between the levels. We're going to see a peak at the energy difference between E1 and E2 and E1 and E3. And this integral tells you how intense that line is going to be, right? If you think about it in terms of Beer's law, remember Beer's law is absorption equals what? Path length times concentration times absorption coefficient. Of course, the path length and the concentration are independent parameters. There's that absorption coefficient that everybody hates because you got to go calculate it and do linear regression to calculate it. That absorption coefficient is this integral, part of it. Right? Within that absorption coefficient is this. If this comes to zero, then the absorption coefficient is zero. Right? And you can there's actually a formula that allows you to calculate this integral for any system and then take it, put it into a system that is thermalized and like the liquid version of this, and you can calculate the actual absorption coefficient. This is another term for this that the analytical people use is absorption coefficient. Intensity is the absorption coefficient. Okay, so not surprisingly, it's an extremely important part of spectroscopy is the intensity. It's what tells you how strongly something absorbs or emits given a stimulus. So the important thing that I want to say, just final word, and we'll get out like 8 minutes early, which is crazy, is that you learn something about the structure of a system in the space that it's in and its wave functions by looking at the selection rules, right? We're going to look at different problems as we go through this. We're going to look at hydrogen. We're going to look at the spring, for instance. We'll look at fitting tops. They all have different selection rules. And so by understanding the selection rules, you can understand a spectrum, which tells you something about the chemical and physical structure of the system. Okay? So it's an essential part of our interpretation of the spectrum. And we're always going to be asking questions about selection rules when we come up with a new problem. Okay? Have a lovely weekend. I'll see most of you tomorrow. If you think this is interesting, take spectroscopy next spring. I have simulations for this, all sorts of cool stuff. Pretty pictures.